Yes, and we're going to get into that today. Yeah. Okay, so last class we had talked about the electrons, and we had said that the total number of electrons in any given atom are going to be separated into two different flavors, right? What are those flavors?
Core and valence.
So we have core electrons and we have valence electrons, right? So core electrons are always going to be the electrons that are from a previous row, right, or period. The valence electrons are always going to be the electrons that are in the same row, right? So for example, germanium has how many core electrons? That's Ge.
18.
18. How did you know that one, Carlos?
Because it's the last, the previous noble gas.
Mm-hmm. So we can always look to the noble gas from the previous row to figure out how many core electrons somebody in row 4 has, right? So if we're in period 4, row 4, right, our previous row's noble gas has 18, which means that we have 18 core electrons. Everybody okay with me? Cool. Now, you could take 32 and subtract 18 to find the valence electrons, but I just like to count across because doing more math is a guaranteed way for me to mess something up. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 valence electrons in germanium. Everybody okay with me there? Coolsies. Questions about that? Should we do another one?
You said 14?
I did say 14. Yes.
Isn't it 4 valence electrons?
So it depends on how you're counting them. I'm including, whenever I'm talking about valence electrons, I'm including the transition block electrons. But there are times when we don't include those, and we'll talk about that when we get into the electron configuration, right? But generally speaking, if I'm asking for the number of valence or the number of core electrons, right, that's what I'm referring to, okay?
Well, how many total electrons would it be? Would it be 32?
32, exactly. And hopefully 18 and 14 equals 32. Right? That's another way that you can... So another way that you can check, right, is, so we said there was 14 valence electrons and 18 core electrons. The core and valence added together better equal the number of total electrons, right? You guys always get to do my grocery shopping with me. Questions about that? We do another example?
Yes, please.
How about, let's do zirconium. How many core electrons does zirconium have?
36.
Sorry, which one?
Zirconium, ZR.
18.
So zirconium is in row 5.
36.
So we'd go to the previous row and we'd have 36
Yes.
core electrons, right?
So it would have 4 valence electrons.
That's exactly correct, Yvonne. Right? So we would have 4 valence electrons, right? 1, 2, 3, 4. And we'd have 36 core electrons. Okay? So just
I don't think I'm understanding the 36. Or like, how do you know that it's going to be that one?
So, because we're talking about, when we're talking about core electrons, we're talking about all of the electrons from the previous elements, right? So everybody that came before row 5, all of their electrons are going to be core electrons, okay? So you can think
So
about,
all of theirs are 36? No.
if you're in row 5, everybody that's in row 5 will have 36 core electrons, right? And then depending on who you're talking about, right, they'll have different numbers of valence electrons. Does that make sense, Vanessa? Kinda?
Sorry, yeah, kind of.
So if I was in row 4, right, then I know all of the electrons from the previous 3 rows will be represented in argon,
The 18.
right? So everybody in
Okay.
row 4 has 18 core electrons, right?
Okay.
Everybody in row 3 has how many core electrons?
10.
10, exactly.
Okay. Okay. Okay.
Yeah. Cool? Okay, so then we were talking about the housing for different electrons. Sorry, I'm checking the chat. Electrons are the same as the number of protons. Yes, the number of protons and the number of total electrons are the same if we're talking about an atom, right? Because atoms are always neutral. So we're not talking about ions yet, okay? But the reason why it's so important for us to talk about sorry guys, I gotta mute you. To talk about the electrons is because that's where all of our chemical reactivity happens, right? So literally nothing about, at least the majority of the chemistry that we'll talk about is really just based on transfer of electrons, sharing electrons, how many extra or how many less electrons you have than you'd normally have, right? So the big story of chemistry is all about electrons. So that's why we're spending so much time talking about this. Okay, so we said that row 1 is going to have 2 electrons in it, right? We said row 2 has how many?
8?
8. Yep, you got it. Row 3, also 8, right? Everybody okay with me still? Row 4,
18,
18. Row 5,
18,
Now row 6 is where things get a little weird, okay? So we have these 2 blocks down here, right, which have all of their electrons and technically go in here, but they make the periodic table really hard to look at if it's really, really long. So we put them down here towards the bottom. But this row has an extra 14 electrons, right? So here we had 18. 18 plus 14 gives us
32.
32, right? So we have 32 electrons in row 6, and in row 7 we have also 32 electrons. Everybody okay with me? Cool. So now we want to talk about electron housing. So I'm going to draw a very ugly periodic table.
Sorry, really quickly.
Yes.
Just wanted to check because adding 14 to 18. Is 18 the max number of core electrons? Why aren't we going down to 36 and 54 on the bottom rows?
I'm not sure I understand your question.
So each row, the number of core electrons is representative of the last element in the row before it,
Right.
correct?
Mm-hmm.
But as we get down, does the number cap out at 18?
No, absolutely not. So if we look at going from xenon, right, to radon, how many electrons did we jump?
32.
Exactly, right? Does that make sense?
Yeah. Can you go back over the added 18 electrons then? I guess I didn't get that.
So we said row 5 and row 4 have 18 electrons, right? And we said row 6 and row 7 have 32 electrons each. Picking up what I'm laying down?
32 core electrons?
Valence.
Valence. Okay. There's the mistake. Thank you.
Yeah. So when we're talking about a particular row, we're always talking about valence electrons. If we're talking about core electrons, it'll always be the sum of the previous rows, right?
Perfect. Thank you.
Uh-huh. Okay. So, not to get too cluttered here, this is my horrible, ugly picture that you guys are going to love. So we talked about the different rows, 1, 2, 3, ... right? As being like different floors in terms of housing, right? So the housing that electrons have, we have a certain floor, and each floor has an associated number of electrons, right? So we said floor 1 has 2 electrons, right? Floor 2 has 8 electrons. My drawing is very bad. Floor 3 also has 8 electrons, right? So again, that's how we're talking about the floors. Now we're going to talk about the housing blocks, okay? So this is called the S block, okay? This is called the D block, and this is called the P block. The one down there at the bottom is the F block. We're not really going to flex on that too much because we don't need it. So, the S block can always hold up to 2 electrons. The D block can always house up to 10 electrons. And the P block can always house 6 electrons. Again, my picture is very bad, but hopefully you guys can work with me. We'll talk about it in just a second, Maria. I just want to give people a second to write this down. Is everybody with me? I'm going to go back to the pretty periodic table because this is ugly. So, when we're talking about hydrogen, right? Hydrogen is in row 1, right? And what block?
S.
The S block, okay? Everybody all right with me there? Mm-hmm. How about lithium?
S block.
Row 2, S block, right? Everybody all right with me? Mm-hmm. Cool. Talking about lithium, we said, sorry, that's my partner. I took over the room before he was ready. We said lithium has how many valence electrons?
1.
One valence electron, right? One valence electron because it's in group 1, right? Everybody okay with me there? So, that electron, the valence electron, lives in the 2s block. So now we're going to start into electron configuration. So electron configuration, oops, sorry guys. Electron configuration is just a fancy way of saying where do the electrons live? Okay? Where are they housed? So, I'm going to just go through and we're going to do the first few elements on the periodic table. We're going to do them all. We're going to do the electron configuration for all of them. So, we start off with hydrogen, right? Hydrogen has one electron, and that one electron is in row 1 in the S block, and that's our one electron. Okay, so we have the row number, right? We have the block, and we have the number of electrons in that block. So, let's do helium. Helium has 2 electrons, right? Yeah? And it's in row 1, right? Helium's kind of a weirdo because it looks like it's in the P block, but it's actually a part of the S block. So even though it's represented over here, the reason why it's represented over here is because it is a noble gas, but it also has a maximum of 2 electrons, so technically it could go over here. Okay? So all of its electrons are in the S block. We said S block can have a maximum of 2 electrons.
So, quick question. The valence electrons, those are the numbers that are represented at the top, right?
No. Let's do some more because the first row, all of our electrons are valence electrons, right? There's no such thing as core electrons. So let's do an example where we start getting into core electrons, okay? So.
Well, I'm just wondering how you're finding the valence electrons here. Because you're not subtracting from the atomic mass and the protons, so I'm just wondering, are you just grabbing the numbers from the top?
Mm-hmm.
Like where it's...
So in row 1, there's no such thing as valence electrons and core electrons, right? Because all of them are in the same row, right? So it's only when we get into row 2 or below that we start talking about core versus valence. Does that make sense, Taylor?
I think. I'll just watch more examples. Thank
Cool,
you, though.
cool, yeah. So, lithium has 3 electrons. Everybody okay with me on that? He's there, right? Protons and electrons are the same number, right? So we have 3 total electrons. And we said the electrons that are the core electrons are going to be all of the ones from the previous row, right? So we have 2 of our electrons from lithium are living in the 1s, and there's 2 of them, right? Now in row 2, we're still in the s block, right? And we have 1 electron in the s block, right? These are our core electrons. These are our valence electrons.
Professor, on the previous 2 examples, there's no differentiation between the core electrons and the valence electrons. Are they considered the core electrons?
It's kind of a misnomer, right? Because core electrons imply that they're from a previous row, but there is no previous row when you're talking about row 1. Does that make
Correct.
sense? So those kinds of delineations, those terms, really only make sense when you're talking about atoms that have core electrons or previous rows with electrons versus the outermost electrons or the valence electrons.
Got it.
Cool?
Quick question. I know you said that there's a limit for 2 electrons in the S block. I'm assuming that means like 2 electrons per ring or per housing option.
So in the S block, we have a maximum of 2 electrons, right? So we get a maximum of 2, and then we move on to the next block, okay?
But each of those blocks has a maximum of 2 in the S group.
Correct.
Okay, thank you.
So, what would the electron configuration for beryllium be?
1s2. 2s2.
Everybody comfortable with that?
Does it make a difference if it's a daddy S or little s?
It's a baby S. Good question.
Okay.
Yeah.
Should
And
we
that's
be able
more-
to do this without looking at a periodic table?
No, absolutely not. No, you'll always have the periodic table, right? Always. 1000% of the time. Yeah. That would be really mean. I would never do that to you. Yeah.
Thank you.
Yeah. So it's hard enough trying to figure out what the heck the periodic table is trying to tell you. But as long as you have the periodic table, it's just about understanding how to interpret it, right? So I don't need you guys to memorize everything that's on the periodic table. I just want you to be able to utilize it as a tool, right? Just like a calculator, right? So, okay, so then if we jump across the aisle to this guy, boron, how many total electrons does boron have? 5 electrons, right? And what are we going to start with?
One S2.
1s2.
Two S2.
2s2. Now when we jump over to this side of the periodic table, what's this block called?
P.
The P block, right? So we're still in row 2, right? But now we're in the P block, right? How many electrons do we have in that block?
1.
1. Right?
Can you point it out again on why is it S1 and S2 because of the previous
they belong to the previous boxes, right? Or the previous elements.
So you can think about it, if we're here at boron, right? Boron has one more electron than beryllium, right? So we're just adding on one more electron to beryllium's electron configuration, right?
Right.
Does that make sense? So every element that we jump here, 1, 2, 3, 4, 5, right? We're just increasing the number of electrons, right? And this is how we organize where they're housed.
Yeah, the where I got confused is why are 2 in the S1, 1s, and 2 in the 2s.
Because
we are carrying them from the previous element.
Correct. Yes.
Okay.
Yeah. So we're essentially, every element that we jump to, we're sticking on another electron, right? But where we stick that electron depends on what block we're in, right? And the maximum number of electrons that are allowed in that block, right?
Okay.
Okay.
Thank you.
Yeah, absolutely. So, looking at boron's electron configuration, how many valence electrons does boron have?
3.
It has 3 valence electrons, right? Everybody okay with me on that? And it has 2 core electrons, right? Boron is in row 2. The noble gas from the previous row is helium, right? And helium has 2 electrons, 2 core electrons, right?
Now I'm back to being confused.
We're sticking a lot of stuff together. Let's do some more examples. I think that's the best way to get it. Can I erase, guys? It's okay? Cool. All right. So we did boron. So let's do carbon, right? How many electrons, total electrons, does carbon have?
6.
Right. And where do we always start?
1s2,
1s2,
2s2,
2s2,
2p2.
2p2. Right?
So then it would have 4 valence electrons and 2
Exactly.
core.
Yep. And again, if you're not sure which ones are the core and which ones are the valence, right? The outermost, or the ones that are in the same row number as the element that we're talking about, right, are going to be your valence electrons, right? So this is one way of keeping track of the electrons. And the other way is just visually looking at the periodic table, right? So we could count from lithium, we have 1, 2, 3, 4 valence electrons, right? Those are all of the electrons up to carbon in row 2. So, how about nitrogen?
7 electrons.
Mm-hmm.
One core electron.
So just what? Let's do the electron. We're just going to do the electron configuration of everybody. We're going to do a lot of them.
1s2,
So it's going to be 1s2,
2s2,
2s2,
2p2,
2p3.
2p3, 3.
Oh, 3. So you just add one more.
Yep. What's the maximum number that I can have in the p block?
3.
3. Oh, okay.
Lindsay's got it. 6, right? P block can have a maximum of 6. So let's skip ahead. Right? What is the electron configuration for neon?
1s2,
1s2,
2s2,
2s2.
2p6.
That's right. Questions? We're still doing okay?
Okay, going back to the previous one,
Yes.
from what Juan Carlos said, is it going to be 1 in the core balance and the rest in the no, one in the core and the rest of them in the balance?
All of these guys have the same number of core electrons.
Okay, that's what I thought. That for some reason I felt like that's a rule.
Yes. So, if you're in the same row, you have the same number of core electrons, right? The only thing that changes as you go across the row are the number of valence electrons. Coolsies?
Yeah.
Could you repeat that, please?
Yes. If you're in the same row as somebody, then you have the same number of core electrons. And again, this is the same information that we were just talking about visually, right, with the periodic table. But now we're organizing it a little bit more strictly. Does that make sense?
Visually, so much better.
You like this way better?
Oh, yeah. 1000%.
Don't worry. Don't worry, we're going to make it cuter. I promise, Lindsay. Okay, so now let's jump down a row to this guy. Sodium has 11 electrons. So what will its electron configuration be?
1 is 2. 2 is 2. 2p6.
Now we're in a new row, right?
3s1.
3s1. You guys are doing so well. Yay.
Wait, why is it S?
Huh?
Why is it 3s1? Wouldn't it be P?
Sodium is in the S block.
Oh, yeah, okay.
Mhm.
Makes sense.
Right, so
I was wondering the same question, and for me that didn't clarify. I'm confused. Why does it go like S, S, and then P, and then back to S?
So we have, this is the S block, right?
Okay.
This is the P block.
Uh-huh.
This is
and
the
it cycles back around.
D block.
That's right.
And this is the F block.
Now I remember learning
Yeah.
about this.
Mm-hmm. Yeah, it's probably harder for you guys to remember because I drew such an ugly picture.
Well, I remember a diagram in which they are aligned by block, and then you have to go in diagonal bands across it.
Yeah, so I'll show you guys a prettier picture when we're done talking about this. There are much prettier pictures. I believe there's one in the chapter 2 key terms and definitions. There's a cute one. But yeah, mine is absolutely hideous, but just for the sake of keeping it in video form, that's why I'm doing this. So I apologize, occasionally you'll have to deal with my horrible crude drawings, but I do have nice pictures also. So here,
I have a question.
yes, go ahead.
So say we get all the way to like row 6D block.
Uh-huh.
Will we always start with 1s, 2s2, 2p2? Like it's gonna be no matter what, everything that we've already done before that?
Yep, so I'm going to make it cuter for you right now, Lindsay, because I think in your mind you're like, this is going to go on forever, and I hate that, right? Yeah. So, totally understood, and we chemists are a lazy bunch, right? So now that we're in row 3, right, these are our core electrons, right? Everybody with me there? Whose electron configuration is that?
Sodium.
Just this. Who does that belong to?
Neon.
Neon, right? So we, being the lazy people that we are, don't want to write out this part every time. So we write as an abbreviation neon in parentheses. And we just write the valence electrons outside. This is called the abbreviated electron configuration. Do you like that better, Lindsay?
No.
Let's talk about it. Let's talk about it. That's not cuter?
It is once I like can get it, but right now my brain has to process first.
Cool.
Because I'm too slow. I don't learn as quickly as like learning one time.
Yeah.
Like
you got to do it multiple times. Yeah.
And then that's how it clicks. But like it makes sense, but it's just a slow process.
Yeah. Totally. And what I will tell you guys is that I'm not going to be asking you to give me the electron configurations. Okay. What I'm going to be asking you to do is to see an electron configuration and identify who it belongs to. Okay? Which is a much easier task. I think. Hopefully. Right? Questions? Yeah, the abbreviated definitely makes it a lot easier to look at too, I think. So we could have written the abbreviated electron configuration for nitrogen as well, or any of the other guys that we wrote before. What would the abbreviated configuration for nitrogen be?
Beryllium 2p3.
Helium 2s2 2p3. It's not much cuter, right? So for those first couple, it's not really a shorthand, but when you start getting into bigger atoms, it becomes a really nice shorthand, right?
Why couldn't that one have been helium?
Why couldn't which one be helium?
That one that you just did.
Nitrogen?
Yeah.
It is. He.
Okay.
Yeah, that's helium. That's neon.
So the abbreviated configurations will always rely on or reference the noble gases?
Correct.
Okay.
Yeah. So we just call all of the core electrons, we call that the noble gas from the previous row. Right?
How did you...
Go ahead, Taylor.
Sorry.
No.
How did you differentiate on, like, the... Na, is that sodium, I think you said?
Uh-huh.
That those are the all the core electrons? Did you just look back on the periodic table, or is there a way of knowing just by looking at this electron configuration?
So we jump down to a new row, right? It's row 3.
Okay.
Right? So jumping down to that next row means that everything that came before it is our core electrons, right?
Okay. Okay, got it.
But also you could do visually, right?
Yeah.
So visually we jump down to the next row, right? And so our core electrons come from the noble gas from the previous row, which means our core electrons are going to be 10.
Yeah. Okay. Yeah, I get it visually. It's just looking at the electron configuration that kind of threw me off.
It's not as cute, right? But you're always going to have the periodic table when you're doing this, right? So it's not something where you have to be able to do this without a periodic table, right? It's just difficult for me to go back and forth, right? But that's the fact that you don't have sodium's position memorized on the periodic table is totally fine, right? So again, if you guys don't have a printed copy of a periodic table yet, I highly 1,000%, 1,000,000 times %, please guys, print it out, okay? Because as a visual aid, there is nothing that is as helpful as having a printed copy of the periodic table. This is so much harder to do if you have to flip through tabs every time you're doing this. And on a quiz, you're not going to be able to do that, right? On a quiz, I'm going to give you this, right? But it's going to be small, and unless you have a microscope or, you know, a magnifying glass, it's going to be very difficult for you to see. Much easier would be bringing your own periodic table as a reference. Does that make sense?
How does that work with the proctorial? So if we have our printed one and we're looking down, we're not going to be flagged because...
No, any more than you would be flagged when you're doing work on a scratch paper, right?
Yeah, I guess just because we can't prove that's what we're looking at.
Yeah, I mean, I get that, but also, so there are a lot of other tells in terms of what, so first of all, you guys are locked out of any other browsers, right? So what's the other thing that you could be looking at?
Your phone.
Right, your phone, right? Now, if you're looking at your phone, you're going to be doing a lot more with your hands, right? It's pretty obvious. I know that sounds stupid, but it's not difficult to tell when somebody's doing something with their phone, and if they aren't using their hands, right? If they're not down here using their hands, then they must be using their voice, right? And that's also being recorded. So again, I know that Proctorio is a huge pain in the ass. But I really think that it's the easiest way for you guys to have confidence that your hard work is getting you an A, and nobody else's not hard work is getting them an A. You know what I mean? Because to me, that's the biggest thing, is I just think it's so disrespectful for students to be allowed to not take it seriously when I know you guys are here working so hard. You know what I mean? So I just want you guys to have that confidence. But I'm definitely not trying to be over scrutinized, right? I'm not gonna sit there and be like, what is she doing, right? So, yeah. And there's a question about how this will be written in Canvas. And again, I'm not gonna ask you to write the electron configurations. I'm going to ask you to identify which element an electron configuration belongs to. So let's do an example of that. What element does this electron configuration belong to?
Sulfur.
I got 1 vote for sulfur. Anybody else want to back them up?
Sulfur. I agree.
Yeah.
Yep, I like it.
Wait, what?
So basically, we just add together all of the electron numbers
So 76.
and look for the atomic number.
There are so many different ways that you could come at this. Oopsie.
We better hurry, girl.
I know.
About to die.
I can only get like one lecture's worth of battery time. I can plug my phone in while I'm doing it, but it like ruins the cord. Anyway, you don't care. It doesn't matter. Okay, so let's talk about this. So how did we figure out that this was sulfur? Okay, so
We could either do the walk, which would be the long way, or do what they said, add all the electrons.
so realistically, you don't care about these guys here, right? Because they're core electrons. Who cares? So really all we're looking at is valence electrons, right? Which is these guys. So we know that this element is in row 3, right? Because that's where its valence electrons are housed. We know it has a full S block. 1, 2 in the S block. So we know it's in the P block, right? We have 4 total electrons from the P block. 1, 2, 3, 4 gets us to sulfur, right? Lindsay pointed out that we could add up all of the numbers of electrons in our superscripts, right? That would give us 2 plus 2 is 4, plus 6 is 10, 16, which is also the atomic number of sulfur, right? There are multiple ways that you can interpret this information. Whatever one makes most sense to you, go with it, right? How we doing? We do another example like this?
Yes.
Cool.
Yes.
All right. I'm going to go with the abbreviated this time because I'm getting pretty lazy, all right? So let's do, who does this electron configuration belong to?
Should be calcium.
Anybody?
Calcium.
I love it. Everybody all right with that?
No.
Yvonne, let's talk. So,
I'm so confused.
so the abbreviated always has the noble gas from the previous row, right?
Mm-hmm.
So AR is argon. You with me?
Yes.
And we have 4s2, right? So we're in row 4 in the S block, and we have 2 electrons.
Oh, okay.
Mm-hmm.
Okay, that makes sense then.
Let's do another one. Let's do, this one's going to be a little bit different, and it's going to be annoying, but we're going to deal with it. So, whenever you're dealing with a, my partner is super annoyed with me right now, sorry. Whenever we're dealing with the D block annoyingly always has a row number that's 1 less than whatever row it's in. Okay? So even though this D block is in row 4, we call it the 3D orbital block.
Is it selenium?
Geranium.
So we have, we have 2 electrons from the 4s, right? 10 from the 3D, and then 2 from 4p, right? That gets me to germanium. Cool? Let's do another one.
Nickel.
So we have 2 from the F's, and then we have 1, 2, 3, 4, 5, 6, 7, 8. Questions?
Why is the D block noted with one less row?
Say again?
I'm just curious why the D block is noted with one less row.
That gets into quantum mechanics.
Okay.
So, it's a very long and complicated answer that you don't need to understand. You just need to know that the D block is always one less than whatever row it's in, right? So let's do another example. Oops.
I have a question.
Yeah.
Like when this pops up on a exam or a quiz, are we writing it in the abbreviated form or the long way?
Do you mean the symbol versus the name?
Yeah.
I would accept either in that case.
Okay, thank you.
Mm-hmm.
Would it be ruthenium? Ruthenium?
So we have 2 from the S block here. 1, 2, 3, 4, 5, 6. Yep, that gets us to ruthenium.
Can you do the questions that are on the chat? It's like the K plus or the Ca2.
Wait, what is it?
So, yes. But I just want to make sure everybody's comfortable with this, because the ion questions will not be on the quiz, and that's technically jumping into chapter 3. Everybody okay with this? So on a quiz, you could see one of these electron configurations, and you could tell me which atom it belongs to.
Can you go over this one you just posted again?
Mm-hmm. So we have...
Why is there a 4 in front of the D instead of a 5?
It's always one less than the row that you're in. So when we were in row 4, it was the 3D. Now that we're in row 5, it's the 4D.
And is that for only the D block?
Only for the D.
Sorry, I didn't hear that.
That's okay, yeah.
It is only for the D block?
Yes, correct. It's technically also for the F block, but we're just gonna pretend like the F block doesn't exist. Okay? Because it is unimportant to us.
Thank you.
Mm-hmm. So, getting into the question that Jesse and Sadie were asking. We said that there's one thing that characterizes a metal more than anything else. What is that thing? What makes a metal a metal?
The losing the electrons, that they're good at losing electrons.
That's exactly correct. They are good at losing electrons. Okay? So, when metals form an ion, what type of ion will they form?
Don't metals form like a collective electron field between the atoms?
You're thinking about the metals as a solid. We're talking about them as ions.
Oh, okay.
Cation.
They form cations, right? Or positively charged ions, right? So when you lose an electron, you become positive, right? So, to this question, oops, Ca2+, right? So if we were looking for the electron configuration of calcium as an atom first, right? What would the electron configuration for calcium as an atom be? Abbreviated, because we're lazy.
Argon.
It would be
4s2.
Sorry, guys. So, if calcium loses 2 electrons, right? It's only ever going to lose those 2 electrons from the valence, right? If it can only lose electrons from the valence, then where did those 2 electrons get lost in the electron configuration?
They transfer to the other atom.
These guys, those electrons, right? So if we're talking about, so this was the electron configuration for calcium, right? If we want to make it the electron configuration for the calcium ion, right? For S0, right? Now, I'm pretty lazy, and so I don't necessarily always want to have to write this. These two things would be exactly the same, okay?
Wait, can you say it again? Where did the electrons go?
We always lose electrons from the valence. We'll never lose core electrons.
Okay, okay.
So, if you can...
So they just disappeared.
They didn't disappear, but we haven't gotten to the mechanism by which they're lost. So we'll talk more about that in chapter 3. Right?
Because calcium was 2 positively charged electrons. Is that why we went
because
the
it's a
valence electron?
Because it's a positive 2, right? That means that it must have lost 2 electrons, right?
Okay,
And again,
the answer like AR 4S0 and AR.
Yeah, those are equivalent to me. Yeah. Again, this is not going to be on your quiz, so don't stress out about it, right? This is just a foreshadowing of what we're going to get into in chapter 3 when we start talking about ions, ionic compounds, all that kind of stuff. Questions about what we've talked about here? I'm going to turn this off so it doesn't die.